Hello everyone, welcome back. So in this video we are diving into chapter 2 of the compiler design, the lexical analyzer. This is an important part of the compilation process where the code starts to be broken down for the analysis. So let's take a look at what we will be covering in this chapter. See, for the simplicity I have just divided this lexical analyzer chapter into two portions, that is theory and numericals. These numericals are mainly asked for 7-mark questions. First of all, in the theoretical concepts, we have the introduction to lexical analyzer and some definitions, that is some frequently asked questions, transition diagrams, finite automata, and some regular expressions. And the numericals, we have conversions of regular expression to NFA by using some Thompson's rule, then DFA optimization, NFA to DFA, and regular expression to DFA without converting it into NFA. For today's session, we'll be covering introduction to lexical analysis, the roles and functions of the lexical analyzer, and some important definitions related to the tokens, lexemes, and patterns. And then we'll see the input buffering. Let's first start with the lexical analyzer. See, lexical analyzer is used in the lexical analysis, which is our first phase when our compilation process starts, where the input is completely scanned from left to right to identify the tokens. We have already seen the example in the phases of the compilation portion, right? And then the structure of the token is recognized using the finite automata, which is being constructed using the regular expressions. See, here the token is nothing but a single logical cohesive unit like identifier, keyword, etc. Now let's talk about the role of the lexical analyzer in the compilation process. This question regarding the lexical analyzer and its role is being asked for 3 or 4 marks in the past year papers for the GTU. So let's talk about the role of the lexical analyzer. See, you can think of it as a compiler's first responder. Okay, so it is a first component that handles your source code. Okay, now what is its main job? See, its main job is nothing but to scan through the entire code and break down into smaller pieces, which we call as tokens, right? See, why we are converting it into tokens, right? See, imagine trying to read a massive novel, okay, without any punctuation or spaces. It will be quite chaotic for you to understand. So similarly, the lexical analyzer simplifies the code for the next stages by identifying the each piece's purpose. Okay, for that we have already done the syntax analysis and semantic analysis, where we check the syntax and meaning of the source code. But before that, we need to convert it into tokens. Okay, so here is what the lexical analyzer does. First is tokenization, that is producing the stream of tokens. See, the lexical analyzer reads the code character by character and group this character into logical units, which we call as tokens. Okay, then it removes the blanks and comments. It removes the unnecessary parts, uh, that is anything irrelevant for the compiler, right? Like white space and comments are not relevant for the compiler, it is just for understanding of the programmer. So it makes it easier to debug the code before moving forward. Then it generates a symbol table which stores the information about the identifiers which is encountered in the input. Okay, whatever tokens are being identified, in that all the identifiers are being stored in the symbol table. Then it keeps tracks of the line numbers, that is on which line the token is being generated. Then it reports the error which is encountered while generating the tokens, that is error detection, which is an important role of the lexical analyzer. So it can flag these issues right from the start and making it easier to debug the code before moving forward. So you can say that in short, the lexical analyzer's job is to break down and organize your code, setting a strong foundation for the next steps. See, here is an overview of what the lexical analyzer exactly does. See, this is your lexical analyzer. It is nothing but a scanner that scans the input string from left to right, and whenever the parser demands get next tokens, okay, it gives a demand to the scanner, that is our lexical analyzer, for the tokens, because for parser to construct a parse tree it requires tokens. Okay, so after demanding the tokens, the scanner returns the tokens, and meanwhile the identifiers are being stored into the symbol table. And it is used by the parser also, because all the attributes regarding the identifiers are being stored in the symbol table, like scope, type, storage, etc. Right, then it converts the syntax tree and it is used by the to check the syntax and the rest of the phases of the compiler to convert it into the target code. See, mainly the lexical analyzer performs in two phases. The first one is scanning and second one is lexical analysis, that is generation of tokens. So this was all about lexical analyzer and its role. Now let's see why we have separated this lexical analyzer and parser. Okay, see, this question is not much frequently asked, but it was asked one or twice in 3 marks or 4 marks question, right? So let's just take a overview or a quick view of this, why we need to separate these phases, right? See, we have already know that lexical analyzer produces the tokens and parser uses these tokens. So the first one is modularity and specification. See, lexical analyzer focus on generating the tokens, and this parsing focuses on checking the syntaxis structure of these tokens. So separating these phases makes easy and simple to manage. Second thing is efficiency. See, this lexical analyzer performs quickly because it has nothing to do but to generate the tokens, but parser has to check the structure of the token, so it is computationally heavier. So by separating these phases, we can increase the efficiency of the compiler. Another reason is reuse of the component. See, lexical analyzer is reused because it can be used across various languages by doing some minor changes, because it just had to generate the tokens of from the input string. But parser is language specific, because for whatever tokens it has been generated, it has to produce the parse tree, or you can say syntax tree. So it is language specific. We'll discuss this parsing theory and parser in the next chapter. Okay, so, so therefore separating this enhances the compiler's portability. Okay, so it becomes a platform independent, but if this both are together, then we cannot uh, mention the portability of the compiler, right? Then it will become importable. Then we have simplification of parsing. Obviously, see, a lexical analysis will remove the burden of dealing with this detailed character level operation from the parser. Otherwise, parser has to do this character level operation also, and then form the syntax tree also. Okay, so let's move on to the next topic, that is frequently used terminologies in the lexical analyzer. See, first one is token. As already discussed, token is nothing but a single logical cohesive unit, or you can say the sequence of characters which have some collective meaning, right? So it is the classification for the smallest units in the source code. See, the categories of this tokens are keywords, constants, operators, and special symbols. Then another one is patterns. See, patterns is a set of rules. Okay, we define the pattern of something, right? So it is nothing but a set of rules which is associated with the tokens, and it acts as a blueprint for the lexical analysis to recognize the various types of tokens. Then we have lexemes. See, lexeme is nothing but an actual sequence of character which we will use to match a token in the source code. Okay, so for it is used mainly for syntax checking or the checking the structure of the token. Let's see an example where we'll see the lexemes and tokens. Let's see an example. See, there is some function, let's say void swap, okay, and integer a and integer b. Okay, so in some temporary variable k, or everyone knows this algorithm, say is equal to b and b is equal to k. So this is what swapping is done. Now see, when we are identifying the tokens and lexemes, see here this void is a lexeme. Okay, so when let's make a table. This is lexeme and this is token. Okay, so when I'm seeing this void, see, what was lexeme? It was an actual sequence of characters that was matching with the tokens. So this is my actual sequence of characters, so that is void. And what is my token? This void is nothing but a keyword. Okay, similarly a swap is nothing but an identifier. Okay, then we have opening bracket is nothing but a operator, right? So similarly you can identify this lexemes and tokens. Next we have strings and language. See, string is nothing but a sequence of characters. When you have a empty set of characters, and you say that it is an empty set which is denoted by 5. Similarly, a null string is denoted by this null or an epsilon. Okay, and this represents the length of the string. Language is nothing but a set of valid string which is defined by certain rules or patterns, okay, on that particular strings. That forms a language, as you might have already seen in the theory of computations. In the Then we have several operations on the language: union, concatenation, clean closure, and positive closure. In TOS you must have seen clean star. So here it is also similar to that. Union, so that is L1 union L2, so the set of strings in L1 and L2. Concatenation, L1 dot L2, that is set of strings in L1 which is followed by L2. Clean closure, so L star, it is nothing but the union of all the concatenation of the occurrences of L, that is 0 or more concatenation of L, that is from 0 to infinity, L raised to I. Same way positive closure, but it is 1 or more concatenation of L, and it is 0 or more concatenation of L. Then next we have specification of tokens. So we specify the tokens using regular expression, that is RE. Okay, so that is when a pattern can be matched by RE, the token is being recognized. Okay, whenever we match the regular expression with the pattern, okay, we mainly use finite automata for this and transition diagrams, but mainly it is that when RE is matched by the pattern, we say that the token is being recognized. Okay, so some fundamental terms of the language or the strings, you can see that prefix. Prefix is nothing but a string obtained by removing 0 or more Taylor symbols, right? Let's say for example I have a string, some Hindustan, let's say. Okay, so if I remove this STAN, then I'll get this. So that is prefix, everyone knows that, right? See, second one is suffix, that is a string obtained by removing 0 or more leading symbols, right? So that this one will be suffix. Then substring, so substring is nothing but by removing the prefix and the suffix from the given string. If I remove this prefix, let's say this and this, so this will be my substring. Okay, then sequence, so strings formed by removing 0 or more, not necessarily the continuous symbols, is called the sequence of string. Next we have regular set. Regular set is nothing but a finite set which denotes a regular language, and a set of which can be described by regular expression is called a regular set. Okay, regular expression is nothing but a mathematical symbols which describes a set of strings of some specific language. Okay, for see, let's see a definition. See, I have some set R which is of some regular language L, okay, over sigma, and corresponding regular expression are defined like this. See, if phi belongs to this regular language or the set R of the regular language, okay, see, R is nothing but it is derived from sigma. Okay, if phi belongs to R, then my regular expression will be phi. Okay, an empty set. Same with null, then my regular expression will be null. Then there is some constant which is belonging to that particular R, which is a subset of R. Then R is only A. Similarly, if there are two languages and two regular expressions, then if L1 union L2, then my regular expression is what? R1 plus R2 or R1 or R2. Okay. Then L1 dot L2 belongs to R, then my regular expression will be R1 R2. And L1 star belongs to R, then my regular expression is R1 raised to star. So this is the precedence and association of operators, just for general understanding. See, a clean star, concatenation, and union. So precedence will be 1, 2, 3, first, second, and third, right? And associate, all are left associative. Then we have input buffering. This is one of the important topic which is being asked for 7 marks or 4 marks in GTU. See, input buffering is nothing but a technique which helps the lexical analyzer to handle the source code efficiently. Okay, whenever you are dealing with the large files, instead of reading the source code one character at a time, okay, we can divide the code into blocks or buffers. Okay, so there are two techniques for input buffering. First is buffer pairs and sentinels. See, in buffer pairs, we use some terminologies. EOF. EOF is nothing but end of buffer, which marks the ending of the buffer in or the blocks which we have divided of the source code. Then we use two pointers, that is lex me, begin, and forward. See, this is my some string, okay, or a code. You can say line of some code. So let's see, my lex me is beginning from this, okay, and I'll have a forward pointer over here. So this lex me beginning marks the beginning of the current lex me, okay, and forward pointer will scan ahead until a pattern match is found, right? Then once the next lex me is found, the forward is set to the character at its right end. Okay, whenever we will see that the pattern is being found, then we'll move the forward to the next one, that is one step to the right. Okay, plus one. Then Lexme beginning is a set of character immediately after the Lexme is just found. Okay, when the Lexme just found, Lexme beginning will point to the one from where the Lexme is just found, and forward will be set to the one step ahead to the right end. See, if the forward pointer is at the end of the first buffer, if it is end of the first buffer, then the second is filled with the n input character, and if forward pointer is at the end of the second buffer half, then the first is filled with the n. Don't worry, I'll explain it with an algorithm. See, when we are doing the end of buffer test, okay, we need to identify that if there is an end of the buffer or not. Okay, based on that we can move our forward and Lexme beginning. So if the forward is at the end of the first half, okay, then we will reload the second half. Okay, we are having these two halves, okay, first half and second half. So when this Lexme is at the end of the, this forward is at the end of the first half, okay, I have identified the Lexme and I have to move the forward now, or relocate the forward now. So if it is at the end of the first buffer, then I need to reload this second buffer, and I'll just increase the position of the forward, that is forward equal to forward plus 1 and end. But if the forward is at the end of this second buffer, okay, or the second half, then what we need to do, we need to reload this first half and we need to move the forward to the starting of the first half. Okay, and in rest of the cases we'll just move forward equal to forward plus 1. So this is the end of buffer test. Then the next technique of the input buffering is sentinels. See, in buffer pairs what was happening, that we have to check each time we move the forward pointer that we have not moved off to one of the buffer. Okay, therefore it takes two tests, right, for checking the current character and for the buffer end test. So what we do here in the second technique is that we combine the buffer end test and the test for the current character. Okay, see, so here we introduce this EOF. So we can reduce the two tests to one by when we extend each buffer to hold the sentinel, that is end of buffer character at the end. Okay, so which is a special character that can't be part of the source program, but we can just introduce here to reduce this both step test into the one test. Okay, so we have made an algorithm for that. See, when we will just initialize the forward as forward equal to forward plus 1. Okay, now whenever an forward encounters an EOF character, then we'll begin with the buffer end test, else we will terminate the lexical analysis. And this buffer end test is nothing but what we have already seen in the earlier section, that is this much is our buffer end test. We just check that the forward has reached the end of the buffer or not, right? Now why the input buffer in lexical analyzer is divided into two halves. Okay, why we just divide this into the two halves, the first half and the second half? See, because we get the efficient buffer refill, okay, and the disk input output overhead is being reduced, and we can get the proper buffer and detection, and the pointer management is done effectively. So with this, we wrap up the essential terminologies for lexical analysis. In the next video, we'll dive deeper into some of the mechanics that brings this concept into life, like transition diagrams, finite automata, and a powerful method known as Thompson's construction, which will be used for constructing, like transforming the regular expression to the non-deterministic finite automata, that is your NFL. And this question is being asked for 7 marks. So this will show us how to visualize and construct the patterns, which is crucial for understanding how a compiler reads and processes your code. Right, so if you have any questions on today's topics, please feel free to drop them in the comments, and don't forget to like, and your support keeps me going. So thanks for watching and see you in the next one. Thank you.